Hello everyone. In this section, we are going to learn row echelon matrices and elementary row operations. The goal for this section, actually, we want to solve the linear system just by using the matrix. Okay, the goal. We want to solve linear system, like several equations with several unknowns. Linear system with matrix. Okay, using the matrix. So let's take a look at the first example. This example actually shows us how to solve the two equations with two unknowns. Actually, we did this before, right? But here we just want to redo this. Okay, 1, 2. And this gives us the method in the future how to solve the linear system. So let's take a look at those two equations. If we want to solve this linear system, we can use two methods, substitution and elimination. Elimination means we can eliminate one unknown by adding them together or subtraction two equations. So let's take a look at this one. We can multiply the second equation by 2. Is that right? So let's see. We can multiply the second equation by, how about -2? Okay, by -2. So what do we get now? So 2x minus y equals 1. Second equation multiplied by -2. So -2x plus 6y -2 times -2. So should be positive 4, right? So we do this. Why we times -2? Because we want to add two equations together. Okay, if we just multiply 2, we can subtract two equations. Same thing, but we want to do addition. Now we add two equations. Okay, we add those two equations. We can say 3 and 4. 3 and 4. So what do we get? We can get just when we add those two equations, we can cancel the x. So we get 5y equals 5, and we can get y equals 1. And then we plug into any equation, 1 or 2, we can get x, right? So if we solve the linear system before, okay, when we learn in high school or elementary school, we do this way. Right now, we are going to pick out, let's see, example 2. We are going to pick out all the coefficients and the constant, write down the augmented matrix. Do you still remember what is called augmented matrix? That means we have the coefficients 2, -1, 1, -3, and also include the b, like constant on the right side, right? This is called the augmented matrix. And right now, we just do something same change as the first example. Actually, this is example 2. We solve the same linear system, but we just look at the coefficient and the constant. We just pick the useful number out. We don't include the x and the y. Now let's take a look at this augmented matrix, and we do the same thing. Okay, but we like to change the order of two equations, okay, like this way. So we change the first row and second row, switch the order, 1, -3, -2, 2, -1, 1. In the future, I will let you know why we always like to do this way, okay? In the future, I will show you why. The first step, we interchange two rows. Next step, okay, we do this way. Next step, we use the first row times -2, add to the second row. The first row doesn't change. The first row still keep the same, but for the second row, we use the first row times -2. Add to the second row. So 1 times -2 added to the second row becomes 0. negative 3 times negative 2, 6, add negative 1, so 5. Negative 2 times negative 2, 4, 4 add 1, 5. Look at this. And the next step, we can divide the last row, the second row by 5. Let's row divide by 5. So again, 0, 1, 1. So 1, negative 3, negative 2. And this, actually, if we look at the second row, this just means so y equals 1. So in the future, don't worry too much right now. So I just want to give you some brief idea. So in the future, we're going to do just some change of the matrix, and we can change the matrix into an easy form, and then we can find the solution. So next, I'm going to give you the definition. It's called row elementary row operations. Actually, what we did here, they are all row operations. Okay, row operation, like we interchange two rows, we divide one row by some number, and then we multiply one row by a number, add to another row. They are all called row operation. So let's see, definition 1 is called elementary row operation. So elementary row operation has 3 operations. Okay, the first one is called PIJ. That means permute the i's and the j's rows in A. Permute 2 rows, or we can say interchange 2 rows. Same thing. Permute. Because in general, in our example, we only have first row, second row, right? But in general, we have maybe i's row and j's row. In A. Okay, this is called first row operation, means interchange the order of 2 rows. Second, MIK. So what's the meaning of this one? Means multiple the k row by multiple the i's row by a number k. So multiple every element of i's row by number k, constant number k. So this is like in our example 2, for the second row, we divided the whole row by 5, right? So we can also think that the whole row times by 1/5. Same thing, okay? So usually, we just do multiple the whole row by a number. It's called MIK. And the last row operation, so we have 3 row operations. The last one is called, notation is AIJK. So what's the meaning? Add. So we use a constant k times i's row, and then add to the j's row. So add to the elements of j's row of A, the scalar k times, k is a constant, the corresponding elements of A i's row. For example, if we have like AIJK, AIJ, the last row operation is like this: 1, 2, 3. If we have, suppose this is S row, this is J row, and if this is 0, 1, negative 2. If we want to use the first S row, if we times, for example, times 2, and add to the second row, and then they become what? 1, 2, 3 become the second row. 1 times 2, add to 0, 2. 2 times 2, add to 1, which is 5. 3 times 2, 6. 6 minus 2, 4. You can see ith row still keep the same. Okay, the jth row has been changed. Okay, has been changed. This is called row operation, elementary row operation. Actually, we use the last one pretty often. Definition 2. Let's see. Let A be M by N matrix. Any matrix obtained from A by elementary row operation is said to be row equivalent to A. That means if for a matrix given matrix A, if we do several times row operation and we get another matrix B, and those two matrices are said row equivalent. Okay. Any matrix by a finite sequence. Elementary row operations is said to be row equivalent. So it's like when we solve a linear system, we can interchange two equations. We can multiply equation by a number, right? We can just look them as row operation. And after those kind of row operations, if we look at the linear system, actually we didn't change the linear system. They still have the same solution. But if we look at the matrices are row equivalent. Okay, so let's take a look at theorem. Systems of linear equation with row equivalent augmented matrices have the same solution set. Solution set. So if you look at the first example, we did several row operation. So you can see actually this and original, they have the same solution. Okay, same solution. And after the next, so we get 2x minus y equals 1, and the last step is 5y equals 5. They still have the same solution, right? And they are all actually row equivalent, okay? Because we just did some row operations. Now let's take a look at the example 3. Let's take a look at this linear system. This is an easy one, but this gives us some idea in the future how to solve the linear system. Okay, give us the method. Let's take a look at this linear system. If we look at those three equations, we know there are 3 unknowns, right? But if we look at the last equation, okay, last equation, x3 is already given. Okay, so we can write down solution. It's like x3 equals 2. It's given, right? And then we plug x3 to the second equation. We can solve for x2 because in the second equation there is no x1, only has x2 and x3. So x2 equals what? 3x3 plus 5. And plug in x3. So 3 times 2 add 5 should be 11. Right? So right now we have x2, x3 and then we plug x2, x3 into the first equation. And the first equation, let's see, x1 equals what? Solve from the first equation for x1. So x1 equals negative x2 plus x3 add 4, right? From the first equation. So from the first equation, we can solve this. And we plug in x2 and x3. x2 is negative is 11, so negative 11, add 2, add 4, so x1 equals what? x1 equals negative 11, add 6 should be negative 5. Okay. So let's see what is the solution. Solution is x1 ordered, okay? So x2, which is 11, x3 is 2. Now, if we look at the augmented matrix for this one, let's take a look at the augmented matrix. So we write down the coefficient here, 1, 1, negative 1, 4. And here, x1 has no x1, so it should be 0, right? And 1, negative 3, and 5, and 0, 0, 1, 2. So in the future, you can see if we can get a matrix look like this one, so that means x3 is just number 2. x3. So this column means the right side of the equation, and here just means x3 equals 2. And then we can solve for x2 and solve for x1, right? So we like to get some equation like this kind of matrix. This matrix is good because we can solve the system easily. So in the future, our goal is this. Want to get this kind of matrix. And then use the method in this example to solve for x1, x2, solve for other unknowns. Actually, this method is called back substitution. So it's just like we keep plugging them back. So we get x3, plug back, get x2, and after that we plug back into the first equation, get x1. So it's called back substitution. And we want to kind of get this kind of matrix, and actually this kind of matrix has a name. It's called row echelon form. Let's see definition 3. Row echelon matrix. An n by n matrix is called a row echelon, okay, matrix. If it satisfies those conditions. Three conditions. Let's take a look at what the conditions. Okay, if we look at this matrix, it's like an example. You can see what the matrix look like. The first one, if there are any rows consisting entirely zeros, then that row has to be at the bottom of the matrix. Okay, so let's see if there are any rows consisting entirely of zeros. Then those rows have to be at the bottom of the matrix. Then they are grouped together at the bottom. The first condition. So what's the meaning of that? So if we have 3 by 3, it's something like this. If we have a row with all zeros, it has to be bottom. So we cannot have 1, 2, 3, 0, 0, 0, and the other something number. This cannot be this case. Okay, it has to be at the bottom. The 0 row has to be at the bottom. The first condition. Second condition, the first non-zero element in each non-zero row has to be 1. If you look at the first number in each row, it has to be number 1. Okay, so the first element actually has to be non-zero element. In any row is 1. Okay, the first number has to be 1. Then next condition is called the leading one of any row. So look at this matrix. I circled those ones, right? So they are called the leading one. Okay, those leading one. And if you look at this matrix, what's the property it has? So the second row, the 1 is on the right side of the 1 in the first row. So it's kind of like in this order, right? So it's like all the ones like 1, 1, 1, like in this order. So the last condition means the leading one of any row, the leading one of any row below the first row is to the right of the leading one. Of the row above it. Don't worry about definition. I'm going to show you some example. We are going to look at several matrices, and from that matrices, and from those examples, we can tell if a matrix is a row echelon or not. Let's take a look at example 4. I'm going to give you several. Okay, let's take a look at this one. 1, 92, 3, 7. Let's take a look at this matrix. Firstly, there's no 0 row, so the first condition is okay, right? So no 0 rows. And let's see. Second condition is the first number in each row, they are all ones. 1, 1, 1. Right? And any row, the leading one of any row is to the right side of the leading one above it. So you can see this is on the right side of that one, and this one is on the right side of that one. Right? So satisfy all the conditions. Actually, this is a row echelon. Okay, so this is row echelon. Now let's take a look. This one, 1, 91, 6, 5, 9. No matter how big is the matrix, we just look at, all the conditions. This number is 1. 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. Is this row echelon? Let's take a look. Okay. In this matrix, there is a 0 row, but it's okay. It's at the bottom. So the last row has all zeros is at the bottom. Okay, that's good. And next, let's take a look at all the leading ones. Is the first number 1 in every row? So 1. This is 1, 1, 1. Okay, they are all on the right side of the row above it, right? This is row echelon. Actually, let's take a look at this one. It's 3 by 3. Okay. First number, non-zero number is 1 in the first row, and the second row, third row, they are both zeros, but they are grouped at the bottom. So this is row echelon. Let's take a look at one more, and then we do the exercise. Is this row echelon form? So let's see. They have each row has leading 1, 1, 1. But the last row list is not on the right side of that one, right? So this is not row echelon form, okay? Because it doesn't satisfy the third condition. Now let's take a look at the example. 1, 1, 0. Exercise, okay? Please tell they are row echelon or not. Okay, please try this by yourself. Actually, the first one, yes. Okay, because we have leading 1, we only have one leading 1, and the 0 rows at the bottom. And this one, 1, 1, 1. Yes. Okay, all the leading ones on the right side of the leading ones above it. So that's correct. So both are row echelon form. So now we know what is echelon form. Next, we want to change our matrix into row echelon form by using the elementary row operations. After that, we can solve the row echelon matrix solution, and then that solution is same as the original linear system. Okay, so that's our goal. Now let's take a look at example 5. We're going to use row echelon elementary row operations to reduce a given matrix to row echelon form. So this is a 4x4 matrix. This is a very important example, maybe the most important example in linear analysis. Okay, because in the future we are just going to do row operations for all the linear system. Okay, so we are going to use this a lot. Firstly, let's take a look. We want to reduce to row echelon, so we need to know, in our mind, we need to know what is row echelon matrix. What's the row echelon look like? Okay, row echelon has leading 1 in each row, right? And let's see, which row has 1? Only the second row has 1. Is that right? So we want to, row echelon form look like what? Should be like 1, 1, 1, 1, like this kind of thing. If after row operations, and here should be 0, 0, 0, and 0, 0, 0, 1, something like this, right? Should be, or it's maybe all zeros, we don't know, but at least this number in the first row need to be 1, and then the other leading 1 is on the right side. Should be like that. So, and also recall what is called the row operation. What are row operations? So we have 3 row operations. Interchange 2 rows Pij multiple one row by a number k, aijk times a row ith row by number k added to jth row, right? Now let's see. So first step, we want to interchange the first row and the second row. And for row equivalent, we don't write down equal, okay? We don't write down equal because they are not equal, but they are row equivalent. So we write down like a small wave line like this, small wave equivalent. Let's see. Here, interchange the first row, second row, so we can say P12. In the future, you don't have to write down those things, but right now, in my example, I have to show you what I did. So I interchange the first row, second row. So now second row become the first row. And the second row, first row becomes in the second row position. Okay? And the row 3, row 4, they keep the same thing. 2, 0, 1, 3. Next, what's the row echelon form look like? This number should be 0. Is that right? Okay. And this number should be 0. That number should be 0. Okay. So how to make those into 0? Let's see. That's why we like leading 1, because 1 can times any number and add to, for example, the leading 1 in the first row times -2 add to the second row can make that 2 into 0. Is that right? So let's see. It's like if we use the first row times -2 add to the second row. So it becomes what? The first row doesn't change, keep the same thing, but if we use the first row times -2 add to the second row, 0. Why we times -2? Because this number is positive 2. We want to make that into 0, so we have to times -2. And the next, -1 times -2 become positive 2. Positive 2 add 1, 3. Corresponding, okay, each position. So 2 times -2, -4. Add here, -5. 1 times -2, -2 added to 3, so it should be positive 1. This is row operation A12, -2. Okay. Next, we want to make the first number in the third row to be 0. This number is 3. So we want to make, how to make this orange, this number to be 0. How to make that into 0? So we use the first row multiple which number added to the third row can make that into 0. You can think. Multiple by 4, right? Add to the third row. And same thing, how to make the first row into 0. The first number, so 1, 4 times -2. Okay? Row operation. So let's see. 1 times positive 4 add there should be 0. Add to the row 3. So 1, -1 times 4 add here. So -4 add there should be 2. So we have to think this in our mind. 2 times 4, 8, minus 7 should be 1. 1 times 4, 4. 4 add 1, 5. Is that right? And 1, same thing, 2 the same thing. 1 times -2 add the last row, fourth row, 0. -1 times -2, positive 2 add 0, 2. 2 times -2, -4 add 1, -3. 1 times -2, so which is -2, add 3, which is 1. Okay, So after this row operation, those row operations, we get this kind of matrix. But this is still not row echelon, right? For row echelon, we need this number 3, need this position to be the number 1. Right, we want that to be number 1. So how to change that into 1? Number 1. We can do this way. We know row 3, we have number 2. So negative 2 add 3 can get 1, right? So we want to multiply the row 3. So row 3 times negative 1 and add to row 2. And if we write down notation, it's like multiply by row 3 by negative 1 add to row 2. You can either write either notation, you can write down this way or this way. So doesn't matter too much. And in the future, when you are very familiar with this, you can skip writing the steps. 1, negative 1. So because we don't do anything to row 1 and row 4, so we just write down row 1, row 4 here. And row 3 actually add to row 2, right? Multiple by negative 2 or 1. So row 3 still keep the same thing. Let's see, row 2. Row 3 times negative 1 add to row 2. So 2 times negative 1, and there should be 1. 1 times negative 1 add to negative 5, so negative 6. 5 times negative 1, and there should be negative 4. Okay? So the second row is okay now. So first row, second row, they both adapt. They are row echelon. Next, think about row echelon. What we should do next? We want to make those into zeros, right? Zeros, because they look like 1, 1, 1. Okay, all the number below them are zeros. Okay. Okay, so we do the same as before. The first row and the second row, actually we don't change anything. They are already satisfy the row echelon form. And we use the second row times negative 2 added to the third row. And the same thing, second row times negative 2 added to the first row. So here, let's see, 0, 0. Okay, look at negative 6 times negative 2, positive 12, 13. And negative 4 times negative 2, 8, 8 plus 5, 13. 1, row 2, okay, still row 2. Row 2 times negative 2 add to row 4, so here 0, because we want to make that into 0, right? That's why we times negative 2. And negative 6 times negative 2, 12, 12 minus 9, 3 should be 9. And here times negative 2, so it should be positive 8, positive 1, 9. Okay, do you know what we need to do next step? We can divide the third row by 13 and last row divide by 9, right? Or we can write down like a row times 1 over 13 and times 1 over 9. Same thing. You don't have to write down the steps, okay? You can just do the row operation directly. So right now we just do simplify. It's kind of like 1, 1, 0, 0, 1, 1. Almost a row echelon, but this number next should be 0, right? So let's do the last step. Copy the first 3 rows because they are already done. 0, 0, 1, 1. So 0, 0. How to make this into 1? So use this number to make this into 1. So row 3 times negative 1. Okay. Row 3 times negative 1. Okay. You can write down either way. So row 3 times negative 1 add to row 4. Become 1. And 1 times -1, 0. So you can see the last row is all zeros and is at the bottom. And each row has leading 1 and on the right side of the row above it. So this is row echelon, right? So from this example, you can see we did several row operations and we get the row echelon form. And here we have one exercise. Start from the easy one. The first one. Let's do another one. Okay. Here's the solution, but you should try this by yourself. Okay, at beginning. Firstly, I simplify those two rows. I divide by 2. Both divide by 2. The second row divide by -4. Oh, +4, doesn't matter. You can divide by +4. Maybe that's easier. Okay, divide by 4. Here should be just 2. And then use the first row added to the second row. 1, -2. Add. So this is row echelon. Right, pretty easy. Let's take a look at the second one. Second one, I need the leading 1 in the first row, so I interchange P1, 2. So 1, 1, -2, 1, 3, 2, -5, 2, and 1, 0, -3, 4. I just interchange row 1, row 2. And next, I need to make those into zeros, so I use row 1 times -3 added to row 2, and row 1 times -1 added to row 3. 1, 1, -2, 1, 0 times -3 added to -1, then 6, 6 and 1, -3, -1. So 1 times -1 add there 0, 1 times -1, -1, 2 times -1 +2, 1 times -1, and 4, +3. Okay, almost, but I need the leading 1 in the second row. So 1, 1, -2, 1. So I multiply the second row by -1. So it's like 0, 1, -1, 1 here. Okay, next I need to make this into 0. So use this one, just add to that one. Can make this into 0. So it should be 0, 1, -1, 1, 0, 0, -2, and 4, right? Almost row echelon. I have leading 1s, but here I need a 1. Okay, so how to make that into 1? Just the last row divide by -2. So 1, -2. That's all. So 1, 1, -2, 1, 0, 1, -1, 1, 0, 0. So this is the final answer for this problem. You have to practice a lot. Please do all the homework problems, because for the whole chapter, like this one, this chapter 2, chapter 3, we just use a lot of row operations. Okay, and we can stop here in this section.